Hello, my name is Aaron Bain, and today I'll be talking about the fatigue analysis on a plate. So a little bit of an outline for what I'll be talking about. We're going to start with an introduction, followed by the objective of the project, and then we'll go over the model details, the results and discussion, and we will finish with the conclusion. So it's very important that we analyze cyclic loading and understand how it works so that we'll know how objects and parts will react to it. Cyclic loading can easily cause failure without somebody realizing it, and this can be devastating because it can cause injuries and lawsuits, and is morally wrong for an engineer not to analyze. In an analysis by Kim, McDougall, Campbell, and Green, they analyzed an ART crosstie system, which is Advanced Rapid Transit Crosstie System. This is basically a crosstie in the picture that works for train tracks to hold the two tracks together. It's kind of similar to what I'll be analyzing because it has a square plate here with some other geometry, and I'm analyzing what is more of the square plate section. Their analysis was extremely successful. They found that their crosstie would be able to easily withstand 1 million cycles, which is a very long life for this part. What's going to be different about mine is that I'm going to be analyzing a commonly found geometry. It's going to be a plate with a hole in it. This can be found a lot of times in automobiles in the frames. They'll cut holes in flat steel to reduce the weight of the vehicle. Yet these are still low-bearing parts. I'm also going to analyze and test for the life cycle and factor of safety of this part. So the objectives of this analysis is to find out what stresses develop in the geometry, how many cycles this geometry can endure, and if there's a factor of safety involved and what it is. So a little bit in the model details. Here we can see the geometry where we have a square plate with a hole in the center. This square plate was about 800 millimeters long and about 500 millimeters wide, with roughly 150 millimeter size hole in the middle. We can see that the meshing around the outside is a little bit coarser. This is a uniform cross section. It's very easy for the project to analyze and doesn't require a very fine meshing. We can see that in the center around the hole, we refine the mesh because this is where a lot of the higher stresses are going to occur, and where we're going to see a lot of the more interesting results happening. So here we can see the material properties. I used a basic just carbon steel, one of the basic ones that Ansys has. You can see here we got the density, 7850 kilograms per meter cubed. We also can see the alternating stress, mean stress, which is also in the table, which I'll talk about in a second. We got the tensile yield strength, which is 2.5 times 10 to the 8th Pascal. And we've also got the compressive yield strength, which is 2.5 times 10 to the 8th as well. Our ultimate strength is a little bit higher at 4.6 times 10 to the 8th Pascal. So in our chart over here, we can see the alternating stress times 10 to the 9th Pascals versus our cycles, which is on a log 10 scale. This will be useful later in the analysis when we're talking about our material and what our stresses are as far as how many cycles it can endure. So here we have the loading conditions that we put on this part. So here we have our loading conditions. We can see that on the left side, I used a fixed support. On the right side, I put a force of 100,000 newtons pulling to the right. This is more than likely going to cause higher stresses around the mid region where we have a smaller cross section. This is the loading condition that we used. So the 100,000 newtons was put in fully reversed, so it's going to oscillate. So it's going to oscillate between 100,000 and negative 100,000 newtons for the entire cyclic loading. We also used a mean stress correction theory, the Goodman one, which I'll explain in the next slide. So here we have the equations and software that we used. We used the Goodman mean stress theory, which is basically an estimate of the rest of them, but this one is extremely useful because it actually causes an extra safety in the life estimate because of the way that it's set up. Below that, we have the life estimate equation where we have the number of cycles versus the stress amplitude and the stress mean. For this analysis, I used Ansys 18, and I also used a computer with a quad-core 2.4 GHz processor that had 8 GB of RAM. Okay, so next we're going to go over the results and discussion and how the analysis turned out. So here first we've got the deformation. We can see that we had a very small deformation at 0.16 millimeters, and that's at the right side where the loading was applied. We can see that the deformation moves pretty uniformly throughout, just stretching the metal. This is a pretty typical result for something like this. This deformation is small enough that it probably wouldn't cause any adverse effects in the application of this plate. Also, it would be probably impossible to see with the naked eye, and you probably have to see it through either measuring or maybe possibly comparing to an undeformed plate. Here we've got the stress contour of our plate. We can see that there was a maximum of 105 megapascal, which is 1.06 times 10 to the 8th pascals, which is well below our yield stress of 2.5 times 10 to the 8th pascals. This means that we have approximately a factor of safety of 2 for as far as stress is concerned for this analysis. We can see here that our stress is basically uniform around the outside, a very much lower stress. And where it gets interesting is at the top and bottom of the hole where our stress is the most, which is at 105 megapascals. This is more than likely where failure would occur if this plate were to fail. So here in this picture we can see the life cycles. We have a maximum of 1 times 10 to the 6th cycles, which we can see is almost uniformly the entire plate. This is more than likely not the most cycles that it can endure though, because this is probably a limit that the program put on it, because the stress that is being applied in these points is actually below the stress where cyclic loading will cause failure. Where it will more than likely cause failure here is around the top and bottom of the hole once again, where the stresses are highest. This is extremely localized, and it is a minimum of 3.1 times 10 to the 5th cycles. This will actually be an issue for our design, which we'll see in the next slide, because of the number of cycles that we want this plate to endure. So here we've got the factor of safety contour. We can see it's almost uniformly about a 5 as far as safety factor goes, because it's almost all orange. Up here at the top and bottom of the hole, once again, is the lowest, where we can see the red, where it's 0.82 for a factor of safety. This means that our plate will fail in these points before it reaches the number of cycles that we want it to. Now, the plate might be able to endure the rest of them still even after these 2 points fail, but it's less likely, as we're going to be reducing the cross section, and so the stresses are going to get higher in the other parts of the plate above and below. In order to fix this, we would more than likely need to redesign the plate so that it is either thicker, maybe reduce the size of the hole, or just change the geometry overall. So in conclusion, we had a total deformation of only about 0.16 millimeters. This is extremely small and would be more than likely would have any adverse effects on the plate in operation. We had a maximum stress of 105 megapascals, which is well below our yield stress, so we wouldn't cause failure from that. This is why we had to do a cyclic loading though. We found that the life range was from 3.53 times 10 to the 5th to 1 times 10 to the 6th cycles. Like we said before though, this 1 times 10 to the 6th cycles is more than likely just put by the program, because the part isn't actually going to fail from cyclic loading in those parts of it. We also found that our factor of safety range was from 0.816 to 15. Because of the 0.816, we would more than likely need to redesign the part, maybe thicken up the parts where this higher stress occurs, maybe shrink the size of the hole, or possibly make the plate bigger. Overall, we found that this would be this is a successful test in order to show us where the higher stresses are going to occur and how a plate or geometry like this is going to react to a loading.